Welcome to the physics of a baseball throw, based on a fireball thrown by Yoenis Cespedes when he was on the Oakland A's. Using physics and projectile motion, we can find how far he threw the ball. The projectile motion of a baseball is in the shape of a parabola and moves in both the x and the y directions. It's given that Cespedes throws the ball at a 45-degree angle at 30 meters per second. We can start by finding velocity in the x and the y directions by making a right triangle with 45 degrees as the angle given and 30 meters per second as the hypotenuse. Using trigonometry, velocity in the x direction is 30 times cosine of 45 degrees. Velocity in the y direction is 30 times sine of 45. Cos and sine of 45 are the same, so velocities in the x and y are both 21.2132 meters per second. To find x, or how far the ball was thrown, first we'll find the time the ball was in the air. We can also find the peak height of the ball after finding time. Assuming that there's no air resistance and the acceleration in the x direction is 0 and acceleration in the y direction is just gravity, or negative 9.81 meters per second squared, we can use projectile motion equations to find the time it takes the ball to reach its peak height. At the peak, the velocity is 0, and we solved for the initial y velocity earlier by getting 21.2132. Solving for t, we get 2.1624 seconds at the peak. Since the peak is halfway to the end of the throw, multiplying by 2 gets the total time in the air. After solving for time, we can solve for displacement while using the velocity in the x direction. Since there's no acceleration in the x, velocity in the x stays the same at 21.2132 throughout the whole throw. Therefore, x is 91.74 meters. Remember, given time, we can also find the peak height of the throw, which is 23 meters. Finding peak height will be important when using equations for mechanical energy. Mechanical energy is defined as the capability to do work and is broken up into kinetic energy and potential energy. During the throw, energy is conserved, so initial energy equals final energy. Using the mechanical energy equation starting from the peak height of the ball, final velocity in the y direction can be found, and it should be the same as initial velocity. Mass cancels out because it's the same on both sides of the equation. 23 meters is the peak height, and velocity on the left side of the equation is 0 at the peak. On the right side of the equation, height is 0 because it's the end of the throw, and velocity can be isolated to equal 21.2 meters per second. Torque is another physics topic related to a baseball throw. Torque is the capability of a force to produce rotation, and it equals force times the moment arm of that force about a joint. Torque can be broken up into statics and dynamics. We'll look at statics and the force required by the biceps to hold the arm in place before the ball is thrown. The free body diagram is shown about the elbow joint. The weight of the forearm, the weight of the ball, and the force of the biceps are depicted, as well as the elbow joint forces. The length of the forearm is 45 centimeters, and the center of mass is 25 centimeters, so the moment arms of the baseball and the forearm can be found by setting up triangles and using trigonometry. Moment arm of the biceps is given, and we're trying to find the force of the biceps. Since it's a statics equation, total moment is 0, and the force of the biceps can be isolated. The force of the biceps equals the weight of the forearm multiplied by its moment arm, plus the weight of the ball multiplied by its moment arm, and all of that is divided by the moment arm of the biceps. So the force of the biceps is 135.4 newtons before the throw. That concludes some of the physics of a baseball throw.